Reverse proxy versus API gateway versus load balancer. Understanding traffic management. The three pillars of modern network architecture. In today's complex digital landscape, managing traffic between clients and servers requires sophisticated intermediary solutions. This visual comparison illustrates three fundamental approaches to traffic management, each serving distinct purposes while sharing the common goal of optimizing communication between users and backend services. 1. Reverse proxy, the service address shield. The concept of invisibility. A reverse proxy operates on a simple yet powerful principle: hide service addresses from the outside world. When a client makes a request, they interact with what appears to be the actual server, but in reality they're communicating with an intermediary that forwards requests to the real backend services. How it works. The client sends a request to what it believes is the destination server. The reverse proxy receives this request, evaluates it, and then forwards it to the appropriate backend server. The backend server processes the request and sends the response back to the reverse proxy, which then returns it to the client. Throughout this entire process, the client remains unaware of the backend server's actual location or identity. Key benefits. Security enhancement. Backend servers remain hidden from direct internet exposure, reducing attack surface. SSL termination. The reverse proxy can handle SSL encryption and decryption, reducing computational load on backend servers. Caching. Frequently requested content can be cached at the proxy level, improving response times. Compression. The proxy can compress responses before sending them to clients, reducing bandwidth usage. Common use cases. Web server protection and optimization, content delivery acceleration, SSL certificate management, and basic request routing. 2. API gateway, the single entry point controller. The unified access pattern. An API gateway serves as a single entry point for all client requests, but with a crucial difference from a reverse proxy. It's designed specifically for API management and can route requests to completely different backend services based on the request characteristics. Architectural intelligence. Unlike a reverse proxy that typically forwards requests to similar backend servers, an API gateway analyzes each request and intelligently routes it to the appropriate microservice or API endpoint. This could mean routing user authentication requests to an identity service, payment requests to a payment processor, and data queries to a database service, all through the same gateway entry point. Advanced capabilities. Request transformation. Modify requests before forwarding them to backend services. Response aggregation. Combine responses from multiple backend services into a single response. Protocol translation. Convert between different communication protocols. REST to SOAP, HTTP to gRPC. API versioning. Route requests to different API versions based on client requirements. Rate limiting. Control the number of requests per client or API key. Authentication and authorization. Validate credentials and permissions before forwarding requests. Microservices enabler. API gateways are particularly valuable in microservices architectures where a single client request might need to interact with multiple backend services. The gateway can orchestrate these interactions, handle service discovery, and present a unified interface to clients. Common use cases. Microservices architecture management, API monetization and usage tracking, cross-cutting concerns implementation, logging, monitoring, and security, legacy system modernization. 3. Load balancer, the traffic distribution specialist, the scalability solution. A load balancer addresses a different challenge entirely, distributing traffic across multiple instances of the same service to ensure no single server becomes overwhelmed. This is fundamentally about horizontal scaling and high availability. Distribution strategies. Load balancers employ various algorithms to distribute incoming requests. Round robin, requests are distributed sequentially across all available servers. Least connections, new requests go to the server with the fewest active connections. Weighted distribution, servers receive traffic proportional to their capacity. Health-based routing, traffic is only sent to healthy, responsive servers. High availability focus. The primary goal is ensuring that if one backend server fails, traffic can be automatically redirected to healthy servers without service interruption. Load balancers continuously monitor server health and can automatically remove failed servers from the rotation. Performance optimization. By distributing load across multiple servers, load balancers help maintain consistent response times even as traffic volumes fluctuate. This is particularly important for applications experiencing variable demand patterns. Common use cases: high-traffic website scaling, database read replica management, application server clustering, and disaster recovery and failover. Key differences and decision factors. Purpose distinction. Reverse proxy focuses on hiding and protecting backend infrastructure while providing optimization features. API Gateway emphasizes intelligent routing, API management, and microservices orchestration. Load Balancer prioritizes traffic distribution and high availability across identical services. Complexity levels. Reverse proxy, simplest implementation, primarily concerned with forwarding and basic optimization. Load Balancer, moderate complexity, focused on distribution algorithms and health monitoring. API Gateway, most complex, incorporating business logic, transformations, and comprehensive API management. Scalability approaches. Reverse proxy enables vertical scaling optimizations and basic horizontal scaling. Load Balancer, designed specifically for horizontal scaling across multiple identical servers. API Gateway enables both scaling and architectural flexibility through microservices patterns. When to use each solution. Choose a reverse proxy when you need to hide backend server details from clients. SSL termination and caching are primary concerns. You have a relatively simple architecture with similar backend servers, and security and basic optimization are the main requirements. Choose an API gateway when you're implementing a microservices architecture, you need sophisticated request routing and transformation, API management features like rate limiting and authentication are essential, you want to decouple client interfaces from backend service implementations. Choose a load balancer when you need to distribute traffic across multiple identical servers, high availability and fault tolerance are critical, you're scaling horizontally to handle increased traffic, and you want to ensure consistent performance under varying loads. Modern architecture combinations. Hybrid approaches. In practice, these solutions are often used together rather than as mutually exclusive options. API Gateway and Load Balancer. An API Gateway routes requests to appropriate services, while load balancers distribute traffic within each service cluster. Reverse proxy and load balancer. A reverse proxy provides SSL termination and caching, while load balancers handle traffic distribution to backend servers. And all three together. Large-scale architectures might employ reverse proxies for edge optimization, API gateways for service orchestration, and load balancers for individual service scaling. The evolution of traffic management. This visual comparison illustrates how traffic management has evolved from simple request forwarding to sophisticated intelligent routing systems. As applications have grown from monolithic architectures to complex microservices ecosystems, our traffic management solutions have evolved to match these architectural changes. Understanding these distinctions enables architects and developers to choose the right tool for their specific requirements, whether that's simple backend protection, complex API orchestration, or high availability scaling. Each solution addresses different aspects of the modern application delivery challenge, and the best architectures often combine multiple approaches to create robust, scalable, and maintainable systems.